Today, we're going to switch gears. Technically, today's topic fits within the previous topic, which was numerical integration. We're going to do the anti-integration, which is differentiation. So some present these topics as integration differentiation. Some present them separately. Your homework, at least, is going to be on both integration and differentiation. They're two opposite things. Today, the learning objectives for these lectures, again, we've been trying to put in these learning objectives for every class, for every chapter. You're going to learn, you're going to know how to define the finite difference method, be able to numerically compute first and second derivatives, potentially higher order derivatives if you know the formula, for discrete and continuous data. So you're given discrete data, calculate a rate of change. Okay? Define and estimate the convergence rate of finite difference schemes. We'll learn about that as well. We kind of touched on this in previous homework when I told you to look at the ratio of different errors, and you said, oh, if we cut, you notice that if we cut the spacing in half, the error gets cut in half or by a fourth. So we'll learn where that comes from today. Define what is meant by order of accuracy of a given finite difference scheme, and use the Taylor series to define to derive finite difference schemes, okay? All right, so this morning, went down to Costco in Sandy to get, food, because we eat at home. We go to the grocery store like 5 times a week. We like fresh, produce and stuff. And I just happened to go down to get some baby formula, and, there was this huge line. It went all the way to the tire center in the back. However, being, growing up in a different part of the world, I just cut through the line. I told them, hey, excuse me, I have children. So they were kind enough, so I didn't wait in line. But I cut through the line. They're like, crazy foreigner, whatever. So I went in, and man, people were running and rushing to get toilet paper and paper towels and water and hand sanitizer. Apparently, this thing now costs $50. I'm a moving target right now. I am a moving target. Look at that. I'm splurging now. Anyway, so, but it's a self-fulfilling prophecy, and part of me is saying, you know what? Yeah, let's everyone be afraid and go and, buy as many supplies as you can and hunker down to not spread the virus at all anymore and kind of quench it. Anyway, we'll leave that conversation to the coffee shop. But I wanted to do a problem on the coronavirus, and today is that day. Okay? So what I'm plotting here are the total number of cases from day 0 of the outbreak. I don't know when they started counting and recording numbers. And tracking the cases for mainland China, shown in blue squares, and the world, the rest of the world, shown in orange circles. So, the world includes China as well. Okay, so initially you'll see that the total world cases were predominantly cases from China, because that's where the outbreak started. But then, as within a month of the outbreak, you start seeing the world cases ramp up, and they're going upward, right? Whereas we see, what the Chinese government is doing is actually quite effective, looks like, because the cases are kind of stabilizing. And I think the rest of the world needs to learn from that and just tell people, just go, stay inside, don't go anywhere for like a month, and then that thing will disappear. Anyway, so now my question to you is, you saw that line at Costco, and like, should we go and buy supplies or not? One way to think about this is to ask, well, what is the current rate of spread of the virus? And now I want you to form in groups and tell me, given these data, in principle, conceptually, how would you calculate the spread of the virus, given these data? Come up either with a formula or give me an idea, given I give you these data, maybe take the last set of data by, this was yesterday or like 2 days ago, and, tell me how you would calculate the rate of change or the rate of spread of the virus. Emily.
Are we only basing it off of just the data? Or
just these data. No, just these data. Just given these data. All right, you get 3 minutes. How would you do it? Given things we learned in numerical methods as well. Are you guys texting? Texting each other? I don't mean to pick on you, but you're like the first group in my... You're doing great. Yeah. So also think in terms of what we've done in class. We did interpolation, we did regression, anything that could give you a quantity, something to calculate a rate of change, okay? So we want number of cases per day, right? That's the rate of spread, okay? Do you have a name tag? Will you just write it on a sheet and just put it up here? Yeah, thank you. Okay. We got about a minute. Do we have an answer from the masochistic academic group?
We do.
Okay. Okay. Derivative. Yeah, but how? Derivative of what?
From where you start to differentiate. Oh, from the...
But how do I calculate that derivative? It's a derivative, but how do I calculate it?
So then you set those two equal to... Oh, wait.
Think about that. Yeah. So I need a practical way of how you'd calculate this rate of change, okay? Practical, a way to calculate it. It's a derivative, but how the heck would we calculate that set derivative, okay? Yes, Eric.
When it says the current rate of spread, does that mean across the whole data set?
The world and China. So
Well, does it mean like across the whole?
yeah, because what's going to apply at the end will likely apply across the entire data set. But focus on the current rate, so at the end of the data, by the end of the data. Yeah. Yeah. Okay. All right, we're almost done. Okay, time? All right, do we have any volunteers now that you guys have developed? Jeffrey.
I'm sure it's not right, but you could kind of extrapolate a little bit. So you can take like the slope for the most two recent data points,
Okay.
and then you can compare that
Yeah.
to the slope to the
Okay.
previous two
Okay.
data points.
Okay. So slope. So you're talking about slope, right? So how do you calculate that slope?
You would just rise over run.
Yes. Okay. Okay. Great.
Then
That's.
you add like a second, whatever the change in slope was between the last two
Yeah.
points.
Yeah. That's a correct. It is a correct answer. Any other takers? Connor.
I would make a polynomial regression and then
Regression.
Yeah.
Okay. Do you think it's a good idea to do regression over here?
probably I think a regression might work.
What polynomial regression? So what order?
Probably like a cubic.
Okay.
Probably say a cubic.
Okay. I actually tried the regression. I don't have the plot on me, but it was horrible. So regression would be interesting. The problem is that these things are changing very quickly. So you need something very local. Rather than taking the entire data, you want something that is based on very recent events. Okay, because our behavior is changing as the virus is spreading. We're quarantining ourselves, we're rushing to Costco to buy things. People are crossing the line in Costco. So, behavior is changing, and your derivative needs to be local. So, any other takers? Okay, so cubic spline between two data points, and then do what? Differentiate the cubic spline. Any other takers? Yes. So all these answers, Brendan. Yeah. Oh, okay. I thought. Yeah, I was stretching out. Okay, Emily.
What if I did something like silly and tried to fit like an exponential curve after day 30?
After day 30, so something like more, this would be probably more, I would put a line. I would do regression after day 30. Now you're not, yeah.
Yes. So one thing I thought of is like if we're measuring spread from China to the world, is you can do the subtract each individual data point for the world over China, and it looks like it would.
Sorry, repeat that again.
Like world data point minus China data point for each, right? And then graph that, and then do the derivative of that.
Yeah, but that won't give you, that will only give you the data outside China, right? Which, I want to track, I am interested in the data, the world data or the data outside China. So I would take the difference and take then, the slope. But all your answers were correct. So what we're going to learn today is Jeffrey's method. So what he thought was wrong is actually what we're going to learn today. But the other answers we know how to do. So you could take the last two data points, fit a straight line, and get a formula for the straight line, and then the slope of that straight line is your rate of change. Or take the last three data points, fit a quadratic. Now you have a formula for the quadratic. Take the derivative of that quadratic analytically, and then evaluate that at the last point. That would give you a rate of change, okay? Those are valid. We know how to do these. Today we're going to learn a different method, and there's a reason behind that, which once we get to ODEs eventually. So ideas, essentially fit a polynomial, differentiate polynomial, fit a local polynomial. Don't fit a full polynomial. We've seen with high order polynomials what happens. They get too wiggly. You get a terrible behavior. So don't do that. Or use Taylor series, which is what we're going to learn today. Okay, so you've probably heard of Taylor series. Who's not heard of Taylor series? Okay, Mr. Taylor. So Mr. Taylor developed a series. Essentially what Taylor says, if you give me information about a function, all the information about a function, so its value, its first derivative, second derivative, all derivatives, at one point only. So give me all information about data at one point, I can predict the behavior of that function at a neighboring point. Okay? This is mathematically written as, if I have information at point x0 about a function f, so this could be actually data that you're getting. So if I know f of x0, f prime of x0, f double prime x0, etc., then I can predict the value of the function at some point x in the vicinity of x0. Okay? So f of x is written as function of x0, f prime x0, and so on. Now, I don't know if you've done this before in any of the previous classes. If you take this to approximate, you can use this to approximate functions in practice, okay? So to calculate exponentials, for example, and logarithms. But every term you add is going to improve the behavior of improve the solution. So what I'm showing here is f of x for an exponential, okay, so this is e of x, this dashed line in black, that's the true solution. And the other curves, they're showing terms in the Taylor series. If we take only the first term, f of x0, around x0 equal 1, you get essentially e to the 1, which is this red line over here, it's a constant. Then if you add one more term, f prime at x0 times x minus x0. So in this case, x0 is 1, and f prime of x0 is the derivative of e of x at point 1. And add that term and then plot along x, you're going to get this blue line. And then as you keep adding terms, you see we get closer and closer to the true function. Okay? Now, that's beyond the point, but that's essentially how the Taylor series operates. The more terms you add, the more accuracy you have. Okay? Now, what we're going to do, we're going to take this Taylor series and invert it in a way to allow us to compute derivatives. Remember, we are after rates of change. We are after f prime, f double prime, f triple prime, and so on. And my claim is that we're going to leverage this Taylor series to pull out f prime and f double prime and so on and so forth. Okay? So let's start by thinking of either discrete data or continuous data given to you x and y values. Now I'm switching nomenclature rather than using y. Remember, we used to use xi and yi. We're going to use now xi and f of xi or fi. Okay? So imagine you have a bunch of data points with a bunch of values at those data points going from x1 to xn. And we call the values f at x1, f at x2. And if the data is continuous, you would have a curve like this, for example. For simplicity, I'm going to call f of xi fi. Remember, every time we say fi, that's the function value at point xi. And then we're going to switch between the two. Not to confuse you, but to make sure that you're always remembering that fi is actually the function evaluated at point xi. Okay? So that's what we get. Now, I'm condensing this plot so that we get x values and function values at those points. Okay? Now, given function values, the Taylor series is useful in finding the derivatives of that function. Now, the question is, find f prime given all of these values, and a representative value is at xi. I is an arbitrary point. Could be 1, could be 15, could be 7. Okay? Given xi and fi minus 1, fi plus 1, and so on, given all those values, the question is use the Taylor series to find f prime at xi. Okay? So now if we only know f at xi, and f at xi plus 1, f at xi minus 1, and so on, find f prime at xi. Okay? So now what I want you to do first, we're going to do this together. Rather, you're going to do it. Okay? The first step in achieving that goal is to write the Taylor series of f at xi plus 1 around point xi. Okay? So I want you to go ahead and write that. Pull out a sheet of paper. Do it in groups or individually. Remember, this is the Taylor series. Okay? This is the Taylor series. And only carry terms up to the second derivative and put 3 dots after that. Just put dot, dot, dot. Okay? So I want you to write f at xi plus 1 as a function around point xi. Okay? So we know f of xi. Okay? And we know xi. I want you to write f of xi plus 1 as a function of f of xi. And we're going to see now, although we know fxi plus 1, what we're going to be after is f prime at xi. Okay? So, but first step is just do the substitution. Okay? Let's see, give you 3 minutes. Pull out a sheet of paper. I want to see you writing, please. So no Python here. Start writing by hand. Yes. So these are the previous slides from last year. Once I'm done with the class, so that you don't get the answers, right? Yeah, no. So these slides, I upload them after class. Okay, thank you. Yeah. Okay. In back corner, you're always separated. You guys either move next to Jordan, or Jordan, go hang out with these guys. Okay. And Nathan, is Nathan with you? Okay, but looks like he's doing solo. Okay. Let's see.
Somewhere. I'm getting somewhere.
All right. So remember, xi plus 1, I plus 1 is an index. It's not xi plus 1. It's point xi plus 1. So make sure it's in the subscript. Okay? Yeah. Okay. Very good. Plus dot, dot, dot. Don't forget the remaining terms. Okay? Okay. So around xi, f of xi plus 1 around point xi. Okay? Trust the force, Jeff. You already answered, you already helped us get the right answer for the slope, right? Yeah, trust yourself. Okay. Yes, ladies.
So
Okay.
I'm not sure. We're not sure if this is right. So is x not supposed to be like xi in this case?
So this is correct, but yeah, but this is saying we're developing. If you have 2 points, xi plus 1, which is xi plus delta x, right, and xi, just write the function at xi plus 1 in terms of everything at xi. That's the reason. So we're predicting fxi plus 1 using values at f of xi. Okay, that's the Taylor series. That's the premise of the Taylor series. Okay, so this is correct. All right. Okay. So time. Let's see. Most of you got it. Most of you got it. Okay. The answer is going to be given to us by Katie. Yes. So just describe what would you do, what substitutions would you put here, okay?
Oh, you just substitute x for xi plus 1.
Uh-huh.
But that's the point that you want the
Uh-huh.
for.
Uh-huh.
And since it's around xi, you replace x naught with xi.
Yes, okay. So what Katie's saying is simply we take our formal definition of the Taylor series, which tells us the function value at point xi around point x0 is f of x, is a function of x0. Over here, we're just simply saying find the function value at xi plus 1 around point xi. So we put xi plus 1 over here and xi over here, everywhere. So x becomes xi plus 1, x naught becomes xi. Okay? So let me show you how this turns out to be. Set x equal xi plus 1 and x0 equal xi, and you get this. Okay? Now I'm going to simplify this by noting that f of xi plus 1 is fi plus 1, and f of xi is fi. And then I'm going to make one additional jump by saying that the distance between xi plus 1 and xi is fixed across all the data set. We're going to call this h, or delta x. Okay, let's call it h. So this gives you this nice and compact formula. Okay? Now, we're going to step back for a second and say, okay, we started by saying, Dr. Saad, you told us that the Taylor series, if you are given function values fi, f prime I, f double prime I, etc., then you can predict fi plus 1. But in this case, we actually have fi plus 1 and fi, but we don't have f prime I, f double prime I, f triple prime I. Right? So we took the Taylor series and kind of did a sleight of hand. Said, okay, we actually know, in this case, fi plus 1, right? That was given to us. And we know fi, but what we do not know is f prime I, f double prime I, and so on. But what are we after? We're after f prime I, right? So we said, remember the initial question was, you're given all of these data, fi and fi plus 1, fi minus 1, find f prime at I. So then we said, okay, we assumed we know everything about the function, we wrote the Taylor series, but then we said, okay, we're going to switch the logic now and say we know fi plus 1, fi, we don't know f prime I. So now your task is solve for f prime of I. You got 1 minute. Just solve for it. And put ... whatever is applicable, okay? So you know fi plus 1 and fi. You know h, of course, it's a constant. What you do not know is f prime I, f double prime I, and so on. But I want you to take out f prime I, solve for f prime I in terms of everything else. So take f prime I to the left-hand side as a function of every. Just try it. See what happens. It's not sneaky. It's not sneaky. You know what I'm going to do, Dylan? Okay. Then do it. Do it, and then you'll tell us about it.
Well, because you've got all of this.
It's called the truncation error. It's not. Did you call it crap? Oh, the crap. The truncation crap. No, but I know you're always on track. So
They're saying like, well, why would we solve for f prime in terms of f double prime? But if I'm right, then like them also solve for f double prime in terms of f.
Okay, we're not going to do that. We're just going to say we're going to neglect all those terms.
Okay, never mind.
Yeah, but you're on the right track. So yes, so start by solving for f prime I. So let me clarify. Solve for f prime of I in terms of fi plus 1, and f double prime and f triple prime. Just leave the double prime terms. We're going to deal with them separately, okay? Okay, time. A lot of confusing answers. So some got it, some didn't. Okay, let's see. Brian, Sam, do you have an answer? Okay. All right. Let's see. Eric and the gang in the back. Getting there. Okay. Triads. Yeah, so you just put f prime to the left, divide by h, and take everything to the right. Exactly, so solve for f prime. This is what happens, right? Take f prime to the left, take fi plus 1 to the right. There's a negative sign, you multiply by a negative sign, divide by h. This is what you get, okay? Now, Eric and the team in the back, they said, okay, then we develop a formula for f double prime, okay? What if we don't? Katrina?
Would that be a negative here?
Because there's a negative fi plus 1 and then negative, and then you multiply by a negative.
Oh,
Okay? So, yeah, there could be a negative sign here, but it's not going to matter because that's, yes? Yes. So what we're going to do next is say, because we're doing numerical methods, and, we already are incurring error everywhere, why don't we just neglect all of these terms? All right? Now, if you remember, that's the definition of the derivative, right? In the limit, as h approaches 0, what do you get? You get the full definition of the derivative. And indeed, the argument here for neglecting those terms is, as long as f double prime is a well-behaved value, it's not infinity, as long as it's a bounded value, as you decrease h, as the spacing of the data decreases, shrinks, you're going to get more and more and more accurate. So that entire error with f triple prime and f quadruple prime, remember, all the other terms are going to be multiplied by h squared and h cubed and h to the fourth. They're going to be even smaller and smaller and smaller and smaller and smaller, right? Eric?
So why don't we just start with the definition of derivative?
Because we're going to get to higher order. Yeah, so we're going to do tricks to get rid of f double prime and get terms where the error is much smaller. You're jumping ahead, but you're right. So, but the definition of the derivative is actually can be defined from this definition. Okay, so we're going to neglect all of those terms and say our definition of the derivative given data fi and fi plus 1, etc. So the derivative at point I is going to be approximated by fi plus 1 minus fi over h, the spacing between I plus 1 and I. Okay? And we're going to call everything we neglected error, an error. 1 over 2h f double prime plus 2 over 3, 1 over 3 factorial, f triple h squared, f triple prime, and so on and so forth. Okay? So bear with me now, and we'll see where that's going to take us. Okay, so we're going to call this error 1 over 2h f double prime, and so on. And you can show that that entire error is dominated by the first term that has h in it. And if all the derivatives are well-behaved and bounded, which is the case for the vast majority of data and cases, then we can, in that entire error, we can show that it's less than or equal to a constant times h. And we call that entire error, we call it order h. We'll define that in a second, okay? But then that gives us the exact. So notice up there I wrote an approximate sign, f prime I, as approximately equal to fi plus 1 minus fi over h. And over here I'm putting a full equal sign because I'm accounting for the error. So this is one way to write it, a rigorous way to write it. Say the approximation of the derivative of f is fi plus 1 minus fi over h plus an error of order h. We'll define what order means in a second, but first I want to geometrically explain to you what's happening here. So if you take these data and assume you know the true error, the true derivative, so the true slope would look like this, right? At point I, this would be the true slope. The slope is tangent to the curve at point I, correct? Okay. So what did we do when we did the forward difference formula? By the way, this is called forward difference, okay? Because we are using, so I forgot to mention that in the previous slide, okay? This is called the forward difference formula because at point I, we're using data from the next point, from the forward point, okay? From I plus 1, okay? Rather than using, so we're using points from I plus 1 and point I, so we call this the forward difference formula. Now, geometrically, if this is the true slope, what does the forward formula give us? It gives us this prediction, okay? Because at point I, it's using point I plus 1 and point I. It doesn't use any data from previous points, okay? So it's always looking forward, so the derivative, in this case, there's a huge error over here. But as we shrink h, we're going to get closer and closer, okay? Now let's go back to this error. We said that the error is less than or equal to a constant times h, and we call that order h, okay? What do we mean by order h? What is meant is that an error of order h means that if h is cut by half, so if you shrink your spacing, then the error is going to be cut by half. If h is cut by a fourth, then the error is going to be cut by a fourth. Okay, that's an error of order h. In fact, this order h is nothing more than the truncation error that we defined in the first few lectures of class. This is truncation error. We took a full mathematical expression and we truncated it because we didn't know how to calculate those terms. So we may as well just cut them up. But an assessment of that truncation error is that it is of order h. Now what that means is if the error at spacing h is ch, then the error at spacing h over 2, so if you cut the spacing by half, it's equal ch over 2, which is eh over 2. So if you cut the spacing by half, you cut the error by half. Same thing, if eh over 4, it's eh over 2, and so on. Okay? Great. Now, in general, and we're going to see this shortly, an approximation is said to be of order p if the truncation error is what? Less than or equal to a constant times h to the power p. So let me repeat. In general, an approximation is said to be of order p. And what does order mean? Order of accuracy. Because we can link this to actual accuracy, to actual number of precision, to actual number of digits of precision, okay? So an approximation is said to be of order of accuracy p if the truncation error is this O sine h to the p, or in other words, the error you're committing in your calculation is less than or equal to a constant times h to the power p. Okay, that being said, show me that if a method is order h squared, okay, then the error will be cut by a factor of 4 if the spacing is cut by half. Got 2 minutes. So remember, remember E, in this case, E is ch squared, right? That's the definition. So cut the spacing in 2 and show me that the error will be cut by a factor of 4. Write it down. Write it down. It will be very clear once you write it down. Just think in terms of error.
So like if your error at h is ch, and your error at number 2 is
Doesn't make sense?
No, I said it makes sense though, right?
It makes sense, but how do you prove it? Just write down E equals ch squared. Okay, this is a, don't write mc squared, E equal mc squared. Sorry, pun jokes. Okay, E is equal CH squared in this case. Cut H in half and show me that the error is going to be cut by a factor of 4. You got it. Okay, you did. Show me. Okay, very good. Kevin, Andy, and Emily, Ronald McDonald team. You got it. Good. Good. You guys got it. You always got it. All right, back corner. You got it. I really like this. It's pretty trippy. Okay. All right, time. All right, so how do we do this? We simply take the definition of the truncation error that for a order h squared error, then at spacing h, EH is less than or equal, worst case is going to be equal to CH squared. Then if we cut the spacing in 2, h over 2, then simply put h over 2 over here, and that gives you h squared over 4. So you get CH squared over 4, and CH squared is nothing more than EH over 4. So if you cut the spacing in half, you cut the error by a factor of 4. Okay? This is called a second order method. So from now on, once you hear, oh, they're using a second order method in their code, only means that their truncation error behaves as order h squared. In other words, if they cut their resolution, if they increase their double their resolution or cut their spacing by half, then they're going to cut their error by a factor of 4. Okay, so you get a lot of gains. Compare that to a error of order h, which is a first order method. You cut h in half, you cut your error in half. Okay? Okay. So now I'm going to do one more thing. And hopefully, if you've remembered the agony of what I had asked you probably in one of your homeworks, if you take the logarithm of this error, okay, if you take an error and a method of order h to the p, or a p accurate method, if you take the logarithm of the error, you get log e equal log time constant plus p log h. Okay, so now I want you to plot this curve. Okay, I want you to give me a best guess of what this curve looks like on a log e versus log h plot. Okay, so h is increasing this way, right? And log e is increasing that way. Okay. Log c is a point. So you could start from 0 if you want, or from here. But show me, how does the curve look like? Does it go like this? Does it go like that? Okay, you got 2 minutes. Oh, okay, so what does this mean? You are. Why would the slope be that value? Why? So therefore, we'll write it as y equal ax plus b. Okay. Think about. I'm confusing you with the nomenclature here. Step back and look at the equation. You're plotting log e versus log h. What if you name log e something and log h name it something else? What is this equation? What if you call log e y and call log h x? No. Think about it. You're plotting y versus x. What is y and what is x? What is that equation? Okay? I approve.
Ow, my wrist.
Mm-hmm.
No,
is that a curve or a line?
It's a straight line. It's kind of.
Okay.
It's a straight line.
Okay. Let's do it. Let's do it after class. Let's do it after class. Well, unless there was a quick question. in Python?
Yeah, or no, in latex.
Yeah, we can talk. We can talk after. All right. Okay, time. Let's see. Who thinks it's a who? Okay, I got a few schools of thought in the class. Okay, we're looking at log E equal log C plus P log H. Okay, and we're plotting log E versus log H. Okay, so I've seen such curves, something like this, something like that, and something like this. Who got the lower curve? Okay, who got the, well, I've seen it. Come on, I saw some of you do it. Now you're changing. Okay. Okay, thank you, Jeff, for being upfront about it. What about the upper curve? Okay, nothing. What about the straight line? Okay, so why is it a straight line? Yeah, let's call this, if you call this y and call this a plus px, right? It's just a straight line because we're plotting this is y and this is x. So it's just a straight line with an intercept at a. So that's this guy, log c, right? And most important thing is that this is the slope, p, over here. That's the slope of the line, okay, tangent of the angle, all right? So this is what this does. Now, this type of curve, this type of plot is called the convergence rate of an approximation. So this may be beyond what you're going to see, but you may hear it if you attend the grad seminar, for example. We may show, oh, and this is the convergence plot of our method. All it says is our method is converging at the advertised rate or the slope, okay? Okay, great. Now, let's do some coding activity. I want you to go up to your Canvas and download the notebook with gaps. It's under Jupyter Notebooks, Numeric Differentiation. It's called Numeric Differentiation with gaps, and it also has 2 files for the COVID data. Download them right now, before we get to do the COVID analysis. Okay, let's see. And the question is on the notebook, so I can release the slide. Google Drive. So we'll do this and then we'll take a break, okay? So you should see something like this. We're going to look at coding activity 1. And the question is, for f of x equal e to the x, compute the absolute true error for f prime of 2. Okay, let me change. I did change the question. Sorry. So let me update the question. So I want you to plot. Actually, this is the question. Update your question, please. I want you to plot the. Never mind. I want you to plot the absolute true error. So you got f of x equal e to the x. You know how to compute the derivative of that. It's e to the x. Get the derivative at point 2. And then compute the true error. So that's the true derivative minus the numerical derivative. Okay? And do that for a bunch of values for h using the forward difference formula. Bunch of values for h ranging from 10 to the minus 5 to 1. Okay? And then plot this on a log-log plot. So what we're plotting is log e versus log h, really. That's what we're doing. Okay? So there's your notebook over here. And I started by getting the true derivative for you. Now I want you to define the forward difference routine and use this formula. Okay? F prime is equal to fi plus 1 minus fi over h. Now, in my routine, I'm passing, I call the df dx, right? That's df by dx. Okay, I'm passing it the function. So that's the name of the function. In this case, it's exponential. Could be any other Python function. I'm passing it the point at which we want to evaluate that derivative and the spacing, h or dx, okay? Call it h if you want. So just, what are you returning here? This is the numerical derivative, okay? Remember, xi plus fi plus 1 is f at xi plus 1, and xi plus 1 is xi plus delta x.
So we're passing like an array as x?
You can pass an array. Remember, with Python, for the thousandth time, if you're dealing with NumPy arrays, it doesn't matter if it's a single value or a NumPy array. As long as, so if you pass an array, it's going to return an array, right? But in this case, we're passing a continuous function. That is going to, if the continuous function is based on NumPy, and you pass h as an array, then it's going to return an array, okay? If you're confused about it, try it. You know, we did this in homework 1, homework 2. You got it, Connor? Okay. Excuses, excuses. Okay, almost there. You got it. Okay.
Is this what those variables are? Is that right? Something like that?
Nope. Nope. What are we doing? F is a function. We want to implement fxi plus 1 minus fxi over delta x, or h. Okay? So delta x is h. Okay? So you guys had 2 minutes to finish the entire notebook. Okay? All right. So let me help you with this one. To my routine, I'm passing the function, the point at which I want to evaluate the derivative, and the spacing. Okay? We are basing all of this on saying df by dx is equal f at x I plus 1 minus f of x I over h or delta x. So that's f at xi plus delta x minus f at xi over delta x. Okay? What is xi? It's this value, because we're evaluating df dx at this point, right? So that's your xi. Your f is given to you, and dx is the spacing. So all you do is return literally the formula. F evaluated at x plus dx, so that's xi plus 1, right? Minus f evaluated at x over delta x. You want to change the names, change them. Call these h, call this xi, okay? xi plus h, and then xi over h, okay? So that gives you our definition of derivative. You want to try it? Say df by dx, give it the exponential function at point 2 with spacing 0.1. NumPy is undefined. Okay. There you go. You get 7.77 whatever. The true value for comparison purposes, true val, is 7.38. Now, as we reduce the spacing, we're going to get closer and closer to the true value. Notice, right? I'm reducing the spacing infinitesimally small, and we get closer and closer and closer. Okay? All right, great. So our function works. Now, let's create a set of values for h, because we want to test for different values of h. It would be ridiculous to go and apply this formula for h equal 10 to the minus 5, and then 2 times 10 to the minus 5, and 3 times 10 to the minus 5 100 times. Instead, just create a linear space for h, okay? Gives you all the h values, and we're going to call that formula, okay, at point xi, but for all of those values. And Paul was asking me, is this a NumPy array or not? It doesn't matter. If you give it a NumPy array, it's going to return a NumPy array. Why? Because all your operations are based on NumPy arrays, okay? So it doesn't matter, right? So here's how we do this, okay? H is, let me break it down a little bit. So h is lin space from 10 to the minus 5 to 1. It's got 100 values. If we print h, this is what you get. So we're going to take now our derivative and apply it to this value of h, and that value of h, and that value of h, all the way in one shot. The great thing about NumPy arrays is if all your operations are NumPy arrays, you don't have to even do a for loop. Okay? So we define range of values for h, and then x equal 2. Now, numeric derivatives. Let me move the error over here. So how do we call this now? Same thing as before. Our function is np.exponential. Our xi is 2. Okay, so on point x. And what are our h values? Instead of passing a single value for h now, I'm going to pass an array. And then I expect an array of what? No. An array of derivatives. Okay, who did not get this? So if we pass an array of h values here, so previously we passed one value for h and gave us the derivative at xi for that value of h. Okay? What if you pass two values of h? It's going to give you two derivatives, one for each value of h. Okay? If you pass three values of h, because it's NumPy arrays, it's just going to apply the derivative formula on each value of h. Okay, so let me try it for you. Okay, so if we apply to np.array for two values of h, 0.1 and 0.01, okay, it returned an array with two values. What are those two values? I'm claiming that this one is the derivative with h equals 0.1, and this one is the derivative with h equal 0.01. Okay? So let me prove it to you. Call the derivative df by dx on np.exponential at 0.2 and h equals 0.1. There you go. This whole thing is this guy, right? And then the other one is the derivative at df dx p.exponential at 2 and 0.01, and gave us the same value. But rather than having to call this over and over and over again, we'll just call it in one shot. Come on, guys, we did this before, okay? Okay, so now all we have to do is call this on the entire array of h that we just created, okay? And it's going to return a huge array that contains what? The values of the derivative for h is 10 to the minus 5 and whatever other value, all the way to h equal 1. But those are derivatives. df by dx, you're fixing xi, and you're changing delta x. Okay? Okay, so we call these, let's call them numeric derivatives. Derivs, okay? Now, the error is simply the difference between the numerical derivatives and the true value. And you don't have to do it for one error at a time. You do it for the entire array you don't have to do it for each derivative at a time. Come on, we're programming. You do it for the entire array of derivatives. So I'm taking this entire array of derivatives, and from it, I'm subtracting the true value, and that gives me the error, okay? Or the errors, if you want, okay? Errors, okay? Print errors, that's where you get. Now I want to plot, on a log, I want to plot the error versus h, okay? And what do we expect? A straight line. That's right. We proved this mathematically. And on a log plot, this is going to be a straight line. What's the slope of this line? Yes, what is the order in this case? 1, because it's a first order method. Okay, you can take a break now, right? I forgot the recording. I just pressed it again. Okay, so now we're back recording. Okay, so we can apply this to a discrete set of data. The only catch is we have no control over the spacing, okay? We have no control over the spacing. H, or the spacing between 2 points, is already provided to us by the data. Okay, we have no control over that. Okay? So now, for your activity, okay, we apply this to the entire data. You got individually, I want you to think, what happens to at the last point in the data? Can we apply this formula to the last point? Xn. Okay. I see there are two answers. One of two answers. The answer is one of two, either yes or no.
Okay, I'm gonna.
Can you apply this formula to the last point in the data?
I like embarrassing myself in a healthy sense.
Sorry, Andy, did you have a question? Yeah.
Oh, I was just wondering, it's probably really simple. You just round the order up to the nearest whole number.
Am I rounding what?
For the order, it's just to the nearest whole number, right? Because
Yeah. It's never. Yeah. You're taking the ratio. What ratio are you taking?
oh, the error to the h bar,
Yeah.
the
Yeah.
log plot, and then
Yeah.
I used a polyfilm on the slope.
Yeah. Okay. All right. Who says yes? We can apply it to the last point. It's either yes or no. It's not, okay. We got 3, and Dylan and Prasanna. Okay, we have 5. Okay. Imagine you're right. 5 of you are right. What about the rest of the class? Can we apply it? You're saying no. What about the rest? It's like you don't know, I guess. Okay. So why can we apply it to the end, to the last point? Show me how I can apply it.
So in its current form, we can't, if we instead use the previous point,
How can you use the previous point?
so it would be f of I minus f of I minus 1.
Well, we haven't developed that formula yet, right? So we're talking about that formula. Come on, Conrad. Yes, you're right. You're right. But this formula, the question is, this formula, can it apply to the last point? No. Because it's going to, at xn, it's saying f at xn is f at xn plus 1 minus f at xn over h. But we don't have f at xn plus 1. And don't tell me you extrapolate. We can't extrapolate. You can't create new information out of existing information. Okay? But Conrad says we can develop another formula to, rather than getting data from the point forward, what if the same way we developed a formula to get data from point forward, we can develop a formula to get data from the backward point. And that's how we do this. We write the Taylor series at xi minus 1 around point xi, the same procedure we did. And notice here you're going to get a negative sign over here because xi minus 1 minus xi is negative h, or negative delta x. And then you're going to get a negative sign. You solve for f prime, do the same thing, and then you get what we call the backward difference formula. It is the other side of the coin for the forward difference formula. Rather than using the next point, it uses the previous point. It is also a first order method because the error is order h, so convergence is going to be first order. Geometrically, if this is the true slope, this is the backward difference formula. This is what it gives you. Okay? Now, you may raise the question, okay, because you're all my students, you may raise the question, what about formulas with order h squared? In principle, in reality, yes, we can develop formulas with arbitrary order. But we're going to expect those formulas to use more and more points to increase that order. Okay? So by mixing the Taylor series at fxi plus 1, xi minus 1, xi plus 2, xi minus 2, xi plus 3, xi minus 3, and so on, if we judiciously add them and subtract them from each other, we can develop, in principle, higher order formulas. So this is what you're going to do next. You're going to take the formula at fi plus 1 and fi minus 1, the Taylor series, and you're going to use that. You're going to combine these two to develop a second order formula. In other words, a formula with a truncation error of h squared, okay, using these two formulas. I want you to combine them in a smart way, okay, to get an approximation for f prime at I using fi plus 1, fi minus 1, etc. Okay, and I'm giving you a hint. Your goal is to eliminate the h squared f double prime term. So combine these two formulas in a way to eliminate the f double prime term. Okay? Remember, you're going to be left with a truncation error. Don't worry about that. As long as you can extract f prime, call the truncation error order h squared. It needs to be order h squared. Okay? So it has to be h squared times something. Okay? Try it out. You can add them, you can subtract them, you can multiply them, terrible idea. You can, add half of the first and half of the second. You can add the first twice of the first minus the second. I want, yes, eliminate the f double prime term. You're no longer tired. You're the excited triad now. Like, yeah. Yes.
So, if you do eliminate the h squared f double prime, then we're not going to have any h squareds in the equation.
Try it.
But, so,
What about the h cubed term?
I mean, then we could divide it by h, but
Are you going to divide by h? There's h f prime, right? How does f prime come out? It has to be divided by h, right? Try it. Try it. This is not going to help you because on the exam you're going to be doing something more fancy. Okay? Trust me. No? Do you? That's truncation error. If you don't eliminate f double prime, your truncation error will still be order h. Right? Okay. All right. So some of you already have an answer, an idea. What I'm going to suggest we do is actually subtract these two formulas. Okay? So if on the left-hand side we get fi plus 1 minus fi minus 1, first term here is 0. Second term is 2h f prime. And then the third term goes to 0. Right? And then the fourth term, you get h cubed f triple prime. Now, remember, don't worry about these terms, because as long as they satisfy our truncation order, which is we want h squared, right, we're OK. So then, do the same thing. Move f prime to the left-hand side and divide by 2h. When you divide by 2h, this guy becomes h squared. And that gives you a second order error. And this is what we want, right? So that gives you what we call the central difference formula. It is the highest order, smallest, easiest formula that you can get for a first derivative, because it only uses 2 points. Same as forward method, forward difference, and backward difference. So using only 2 points, we were able to still increase order, cut the error by fourth, right? So that gives us order h squared error. It's called the central difference formula. Okay? I'm posting these slides online, so you'll get all of this information. Okay. Visually, this is going to give us probably the best approximation for the slope. Okay? Okay, great. Now, we have 3 formulas to compute derivatives. So going back to Eric's question, we could have started by defining the derivative, but that would have only defined the forward difference. But then with Taylor series, we were able to get the backward difference. We're able to get a central difference. And then we're going to see we're going to get higher order forward and backward differences. Okay? And we'll see why in a second. Okay? Okay. So now we have enough ammo to tackle discrete data, because the challenge was we couldn't use the forward difference formula, okay, at the end point on the right. So we developed the backward difference formula. But then we realized, well, we can get higher order accuracy with only 2 points. So we developed the central difference formula. Okay? So now given a set of data, what we can do, we tried to use the highest order, cheapest method we could get. So that means whenever we can, we apply the central difference formula. Okay? And that allows us to apply it from point x2 all the way to xn minus 1. But then at the ends, on the left, we use the forward difference. And on the right, we use the backward difference. Okay? And then we're going to use this to do the coronavirus data. Okay? So if you go, if you go to your Jupyter notebook, okay, I want you to, now this is going to be a little bit harder. So I think I'm just going to go guide you through it because we're running out of time. So, but I want you to develop a Python code to find the first derivative of discrete data, given any discrete data, and then apply the code to analyze the COVID-19 cases. your code should use central differencing for interior points and forward and backward differencing for the first and last points, okay? And I'm giving you a template in the Python code over here. Now, what I'm going to do here, we discussed a little bit early on. So first, we'll just load up the data. They're given to you. You know, you can read this while you're drinking tea at home to understand what I did. But this is how I generated this plot that I'm using, that I used in my slides, okay? Now, over here, I'm defining a new routine called df by dx. And in this case, I'm dealing with discrete data, okay? So what I'm interested in for this routine, I want to give it, what does the routine want when you're doing discrete data? It needs the function values, right? The yi, the fi values, and probably the xi values. Now, we said that our spacing is constant, so we could have just given it a delta x. Or, if you want, just give it the entire array of the x values, okay? So that internally, you can calculate your delta x, okay? So what I do internally, your dx, I simply take the difference between the first two values in the xi values. So if you print xi, it's simply 0, 1, 2, 3. So the spacing is constant. In other words, xi1 minus xi0 gives you delta x, or xi10, minus xi9 is going to give you the same delta x value, okay? Now, for my result, I'm going to create an array for my derivative. Remember, this is discrete data, and I want to find f prime at every point of those discrete data. Okay, so my result is going to be an array of equal size to the discrete data. And I'm initializing that array by zeros, okay? And you can do numpy.zeros of size n, but there's another way to say zeros like fi. So it creates a numpy array of the same size of fi, okay? Now we said we want to do something special for the first point and something special for the last point. Okay, we're going to use forward difference for the first point and backward difference for the last point. Agreed? Okay, so for the first point, that's our result, derivative at point 0. We're going to use forward difference over here. How do we do this?
fi of 1
Okay,
minus
fi of 0, correct, because fi is an array, over delta x, over dx. Okay, so that gives us the derivative at the first point. Okay, that gives us derivative at point 0. Okay, now, for the last point, remember the trick with using minus 1? We start counting backwards. We're going to use a backward difference over here. Okay, Connor, you want to take a shot at it?
should be fi of -1 minus fi of -2.
Or, okay, so fi of -1, let's remember the backward difference formula. So yes, the backward difference formula is fi minus 1. So we start with the last point, which is -1, minus the point after that, so that's -2. We're counting from the right end. So that's fi -2, fi minus 1, okay, over delta x, okay? All right, so that gives us first and last point. Now, the problem is with points in the middle, okay? Do you have an answer? Because you always have an answer for these things. Okay. Okay. So, what I'm going to show you here is what we looked at this way early on in class when we looked at slicing, okay, at slicing data. We could do it with a for loop, but Python is smarter than that. So, what I'm going to do, I'm going to draw these data points over here and only worry about the interior points, okay? And I already saying the result at the interior points, so starting for point 1, not point 0, point 1, all the way to the last point -1. So if these are our points, okay. Python indexing, this is point 0, 1, 2, 3, 4, 5, or minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. So that's Python indexing, either way. Okay, that's how you index the array. Now, the array result, if we go from point 1, so we want to apply the central difference. We cannot apply it here. We cannot apply it here. But we can apply it at all these points. So we want this set of points. How do we get that? We use the semicolon. We say we want to go from 1 to minus 1. Now, 1 is going to give you this last point. Minus 1 is not going to give you this guy. It's going to give you that guy because it's an open-ended interval. Okay? We've seen this before, right? So we agree that this gives us the entire set of these points. Now, I'm going to do this again as an array. The central difference says f prime at I is fi plus 1 minus fi minus 1 over 2 delta x. What is the set of fi plus 1? For this point, it's going to be this guy. So we have this point. For this derivative over here, it's going to be this point. For the derivative over here, it's going to be this point. And for the derivative over here, it's going to be that point. So our fi plus 1 is this set. Okay, so how do we get this? Okay, using slicing. It's fi starting from 2 to the end. That's how you slice it, because this is our first fi plus 1, and this is our last fi plus 1. Okay, can you tell me what fi minus 1 is? So we start, for the derivative over here, we need this point. For the derivative over here, this is fi minus 1, this derivative fi minus 1, and this derivative fi minus 1. That's where we're stopping. So we're going to start from here to here. Okay? So how do we do this? We start from 0, which means just nothing, all the way to minus 2. Because minus 2, open interval, is going to give us this point. So that gives us the set of fi plus 1 minus the set of fi minus 1. I'm subtracting two arrays. Okay, I'm subtracting two arrays, or two sets of points. Always go back to this way when you're trying to implement something like this, okay? Over 2 delta x. Okay, now over here I do the rate of growth for the China data, and then for the world data, oops, f is not defined. Where's fi? Fi. Okay? And then when you plot this, this is what you get for the rate of change. So you see, as we get close to the last day for China, we're nearly 0. Okay? But for the rest of the world, there's about 2,500 cases per day. Okay? And that's pretty scary. Okay? So wash your hands, cough in your elbows, Don't travel. I canceled all my travels. We're expecting a child in April, and so there's a high risk for, and we don't want to take any risks. Anyway, so this is how it's done. We'll talk about that later. But I promise we'll get to that. I'll show you pictures, too. Okay. I'm going to see if I can rush through this very briefly, because I want to the rest of the slides are nothing. Okay, so one problem with this approach is we're using a second order method in the middle and a first order at the ends. And what is the weakest, when is a chain is as strong as its weakest link? So at best, we're going to get first order for this data. So we need to develop second order forward and backward differencing. And we can do that, again, using Taylor series. I'm giving you a bunch of formulas here. Okay, this is forward, backward, central. But then this is second order forward. You see how it uses fi plus 1 and fi plus 2. And same thing, second order backward uses fi minus 1, fi minus 2. Formulas applied the same way we talked about. And finally, second derivatives. So we're not going to go through the details of deriving second derivatives. They're a little bit more excruciating, but these are formulas for second derivatives as well. Okay? All right. Well, I wish you a happy spring break. Sorry, we actually finished later than, than usual, but thank you so much for your attention. Good luck, and I'll see you after spring break, okay?